Hey guys, welcome to video 10 of the Magnetism series. In this video, we're going to be taking a look at what's known as the Biot-Savart Law. Now, the Biot-Savart Law is really just a fancy way of saying how much magnetic field is there at some place around a current carrying wire. Now, hopefully you've watched video 9, but if you haven't, I really recommend you go back and do that because it will help you visualize what we're trying to do today from purely a visual standpoint and a conceptual standpoint. Whereas today, we're going to get into the nitty-gritty of actually using calculus in order to calculate what the magnetic field strength is at some point away from a wire. So without further ado, let's get into it. So we're going to start from the very basics here by just talking about a few quick relationships between variables. What we find and what we remember hopefully from the last video is that moving charge generates magnetic field. So if I have a current running through, say, this wire over here, there will be a magnetic field generated around it, given by the right-hand rules that we talked about before. Now, if we set up an experiment where we had an ammeter connected in some sort of a circuit, and we had probably some resistance just so that we can control that, and we had a magnetic field sensor, maybe a Hall sensor, placed right over here, we could vary the current, and we could measure the magnetic field as a result. And if we collected our data and graphed the magnetic field versus the current, we would find a direct proportion for this constant current. So that means that as the current increases, the magnetic field strength increases, and that makes quite a bit of sense, I think. Now, just with a lot of the other laws that we have in physics, some of them fundamental laws like Coulomb's law, the universal gravitation law, and the like, we find that there's oftentimes an inverse square relationship between the field and a position away from the source of that field. And we're going to use the starting point as the same idea in this magnetism equation. So essentially what we have right now is that B is proportional to I over R squared. Now, in order for these to actually be an equation, what we find needs to happen is that we need to add a constant of proportionality. Now, if you remember from, let's say, for instance, Coulomb's law or the electric field, we had a constant of 1 over epsilon naught times 4 pi, or 1 over 4 pi epsilon naught. Epsilon naught was the vacuum permittivity, and it described the space around the charged particle. Well, we're going to have something similar here in magnetism, and that is mu naught over 4 pi. Now, mu naught stands for vacuum permeability, and this is a magnetism constant that we will use quite a lot of times. We'll also see that the connection between the vacuum permittivity and the vacuum permeability constant is actually very profound. So with this constant in mind, and this ratio I over R squared, we would have B equals mu naught over 4 pi times I over R squared. Now, this is unfortunately not complete yet, so we've got to do a little bit more development. In order to do that, I'm going to pull up an example here. And this example is that we have, say, a piece of wire that's connected to other ends that we're not concerned about right now, but there is current running through this wire, and this current is constant. And that actually becomes a very important point as we progress through this idea of the Biot-Savart Law. And what we need to say here is that the current, if it's constant, we're going to kind of group it around the mu naught over 4 pi. So we'll put it here on the left. Now, R squared, we're going to leave kind of on its own here because we've got to add some other information to that in order to get where we're trying to go. Now, let's pull back for a second and just remember what it is we're trying to do. We're trying to come up with what is known as the Biot-Savart Law. Now, Biot-Savart is not one person. It's named after two different physicists. One of them, Jean-Baptiste Biot, and the other, Félix Savart. And what they did in the 1800s was a series of experiments that came up with the relationships that we find. and then also mathematically derived that they agree. Now, what this equation's trying to do at the end of the day is say, okay, here's a piece of wire that has current running through it. What's the magnetic field at point P? Can we calculate the magnetic field at point P or predict what it would be? Now, if we think of a current running through this wire, we know that at every location along this axis over here, we are measuring some value of magnetic field. But this wire is asymmetrical to that plane. And so what we're going to do here is say that even if the wire were not symmetrical, and we just took a straight line example, that's still going to have an effect. So let's say, for example, if I had the asymmetrical wire and I place point P here and I say, find me the magnitude of the magnetic field at this point, what would we do? Well, we couldn't just use the equation or so-called equation that we have right now, mu naught over 4 pi times I over r squared, because r squared is not just this straight line distance between the wire and point P as it stands right here. Now, we will see in some cases that that actually is true. However, right now it is not true, because what you might be thinking, as if you remember to electrostatics, when we were trying to find the electric field at some point away from, say, a rod of charges, every little piece of this current or this current carrying wire is going to be independently contributing to point P. And as a whole, the field is going to superposition, which is just the fancy way of saying add up, to give me a total magnitude at point P. So in other words, what we tend to say here is that every little dl or current element, right, that's the wire current elements total chopped up into lots of little pieces, we're going to say that at any given time, each little current element, which is pointing tangent to the wire, and you can think of that as almost like a little electron velocity, right? It's always pointing tangent to the path that it's taking. Although it's not exactly that, that's one way you can just sort of imagine it, that every little dl piece here is some distance r away from point P. And that is, of course, going to vary depending on what dl location you're focused on. Now, you can see that the variation occurs. There's a different r value here, and that's why I said from before, r squared's sitting outside here right now because it's waiting for us to come up with a way in order to incorporate it to find the full magnetic field strength. Now, what we're going to say here is that each dl value at some distance r away is contributing to a tiny dB value. So every little dl value is not making the full magnetic field, it's just making a piece of the magnetic field that we will eventually sum together. So at this point, we're changing our Biot-Savart law into the following. Instead of B, we're having dB is equal to, and I'm going to pull the mu naught over 4 pi times I out over here to the side. Now I know that I'm going to be summing up little pieces here, and we're going to get to where they come from in a second. In the denominator, I know I'm going to have my r squared value, but I do know that that is a function, right? It's changing depending on the dl location. So I'm going to put that up here that I'm at some point. And now what we notice is that as that r value changes, or as I focus on a different dl location on the wire, I see that there's a slightly different angle here between the dl vector and the direction of r. Now, it's the direction of r that has the angle between dl and r. It's not r itself, right? So in other words, what I can say is, and I'm going to zoom in here, I'm going to say that if I'm just looking at this one little dl piece here, that's that little current element, r points, say, this way. Now, r is a lot longer. It's a full magnitude all the way up to point P. But the angle, whether I consider just a small piece or a long piece all the way to r, is the same. But I need to make sure that I am accounting for the fact that that angle is going to be changing. So I would say that r has a unit vector r hat, which just tells me the direction. Now, r hat, or any unit vector, has a magnitude of 1, so it's not going to affect the answer of the problem in that regard, but it is going to account for the fact that there is an angle between dl and r, and this is actually dl cross r hat. Because essentially what I'm saying there is that at any given time, the perpendicular component of the two is going to be contributing here. Now, we've talked about that before in a slightly different perspective in the beginning of magnetism, so it shouldn't come as a huge surprise. But if we come back to our equation now, we see that we have a formulation that says dB is equal to mu naught over 4 pi times I times dl cross r hat over r squared. Now that's a lot of information crammed into one little equation, so I recommend go back and look at what each of those variables stands for in the equation. Now, we are trying to find the total magnitude at point P, so we know that we're going to have to sum or integrate over each side of this equation. So when I sum up all of the dB values, I get a total B value, and so I have to sum up or integrate the other side too. Now I'm going to pull out mu naught I over 4 pi and then put my integral, and I'm integrating dl cross r hat over r squared. Now I'm going to rewrite this one more time and say that I have b is equal to mu naught I over 4 pi times the integral of dl sine theta over r squared. Now, where did the sine theta come from? Well, we had a cross product, right, between dl and r hat, and the cross product is between dl and 1 sine theta, so I can leave that out, and so now I can see what I'm integrating. Now it becomes a lot more apparent what's actually happening here. Now, clearly what I'd want to do is I would want to put some of these terms in terms of other things. So sine theta or r squared I could write in terms of other things, because we're integrating with respect to dl, right? And so we would have to make some sort of changes if we wanted to use this. But for this video, our main goal is really to come up with this Biot-Savart law. In the next video, we're going to see how we can come up with a special case of this that's a lot more manageable and is the most common one that we will see used. But in this case here, we have the vacuum permeability constant over 4 pi, so a constant, times I. Now that's the major idea. I and B are directly proportional. More current, more magnetic field. And then I'm going to integrate dl cross r hat, or dl sine theta, over r squared. And I can use this now to help me figure out the magnetic field at some point P away from some current carrying material. Come back to the next video and we will take a look at a special case of this Biot-Savart law.